Section 2.2, conditional statements. So we briefly touched on the conditional before. This is where we've got the if, then, and our general form is if P then Q. We can also describe it as P implies Q. Our notation for this is an arrow, so it's P arrow Q. We call the first part P the hypothesis, and the second part Q the conclusion. So if we have if 0 equals 1, then 1 equals 2, while that is a bit odd statement, the way it's set up with the conditional, the statement as a whole is actually true. Because of our truth table, so if we've got our if P then Q, the only time we're going to get a false is if P is true and Q is false. Every other time it is going to be true. And do you notice for order of operations, the if then is performed last, unless of course we have parentheses. So once again, let's see if we can put together one of our larger truth tables. Here's our statement we'd like to look at. Again, as with my other truth tables, I'm going to take each piece individually and work it up until I can get that full one. So here is my solution. Again, we're going to have those left two columns. And you'll notice here I've got that conclusion at the beginning, just because not P is easy. And here is the hypothesis part, P or not Q. And last but not least, I'm going to put the hypothesis implies the conclusion. And here is the result I would get from that. All right, we've seen a couple logical equivalences. Now let's look at some that involve the implies. Again, as with all of my other equivalences, I'm going to do the left-hand side, and then I'm going to do the right-hand side. And since they are supposed to be equivalent, we should get the same result on both the left and the right. And so again, this is a description of how to get that. And here is my big table here. And again, you can see all the pieces I'm slowly putting together to get that. So here is my left-hand side, P or Q implies R. And here's my right-hand side, P implies R, in parentheses, and then also in parentheses, P implies R. And if you look down those last two columns, they are the same for all points. So yes, those two things are logically equivalent. When you do these on the homework, you will be asked, at least for the last two columns, to enter all of those true or falses. And then here we would conclude, yes, they are logically equivalent. Now, as it turns out, I can take an if-then and represent it as an or. So here's my if-then, and the way I'm going to represent it is as not P or Q. So do note again, it's not P first. So if I take either you get to work on time or you are fired, excuse me. So not P would be you get to work on time. Q is you are fired. Again, I've got that little or in between. So, to write it as an if-then, again, I've got to take the opposite there. So I do not get to work on time is not P. And I would write, if you do not get to work on time, then you are fired. And that would be the if-then equivalent of that same statement. All right, we've looked at some negations. Let's look generally at how to negate a conditional. So if we've got that if-then and we'd like to negate it, the opposite is going to be P and not Q. And that is generally something we will want to have memorized. And here we're going to hit a couple laws here real quick just so you can see how it works. We're going to start by using De Morgan's law, and then we've got that double negative, which is what gets us just that P out in front. So let's go ahead and take the negation for each of the following statements, remembering how to do it. So if my car is in the repair shop, then I cannot get to class. So again, the opposite of that will be P and not Q. So my car is in the repair shop and I can get to class. Similarly, if Sarah lives in Athens, then she lives in Greece. The opposite of that, Sarah lives in Athens and she does not live in Greece. And as you can see there, there are some options that would make that a true statement. All right, let's look at something called the contrapositive, and specifically for a conditional. So again, our initial conditional is if P then Q. The contrapositive is if not P, then not Q. So they're both nots, but they're also in the opposite order. And again, we call that the contrapositive. And one thing we want to remember is a conditional is logically equivalent to its contrapositive. That is always true. So let's take some conditionals and write them with the contrapositive. If Howard can swim across the lake, then Howard can swim to the island. So the contrapositive, if Howard cannot swim to the island, then Howard cannot swim across the lake. My second example, if today is Easter, then tomorrow is Monday. So my contrapositive, if tomorrow is not Monday, then today is not Easter. All right, so we've looked at the contrapositive. Now let's look at the converse and the inverse. So the converse, we're switching the order. So if Q, then P. The inverse, if not Q, then not P. So the order is the same, but we've taken a not. And again, we've got those written out there symbolically for you as well. So let's now take the converse and inverse of those statements that we had a few minutes ago. So again, we've got Howard. Our converse, if Howard can swim to the lake, then Howard can swim across the lake. The inverse, if Howard cannot swim across the lake, then Howard cannot swim to the island. With our Easter example, the converse, if tomorrow is Monday, then today is Easter. And the inverse, if today is not Easter, then tomorrow is not Monday. As you can see, these are definitely not always true. So a conditional is not logically equivalent to either the converse or the inverse. However, the converse and inverse are logically equivalent to each other. And those are things we definitely want to remember. All right, so let's now look at the biconditional and the only if. Now, if you see only if, that is understood to mean the same thing as if P then Q. That's just a way we do sometimes phrase it. So if you have a statement with an only if, we do usually go ahead and rewrite it because it's easier for us to see that if, then. And here are two different ways that we could do that. I try not to give you an only if statement. You'll see a few in this homework just to help you get practice with it. But after that, we're not really going to see that only if because it is a little confusing. We will, however, see the biconditional. So the biconditional is also called the if and only if. And we see this a lot in mathematics. You'll notice our symbol for this is our arrows now pointing both directions. And the way we also sometimes abbreviate it is if with an extra F, or if, as I like to call it. And this is logically different than if, then, our regular conditional. And so let's see what that looks like. So the if and only if, we get true if they're both true, we get true if they're both false, otherwise our conclusion is going to be false. And again, for order of operations, we'll do that if and only if last, same as the regular conditional. And as always, we can put parentheses if we need to change that order. So here's just a quick recap of order of operations. So not first, and or comes second, if then, and if and only if are last. And again, that's assuming we don't have any parentheses to tell us otherwise. So let's do a rewrite. This computer program is correct if and only if it produces correct answers for all possible sets of input data. Now again, there might be a couple ways we could do it. My example here, since we want a conjunction, that means an and. So if this program is correct, then it produces the correct answers. And if this program produces the correct answers, then it is correct. So you can hopefully kind of see how we wrote it there as if P then Q and if Q then P. And that is everything in section 2.2.